Hi folks, right, this is the water cycle video number 2 and we're kicking off with something I talked about in the first video but actually is pretty important and worth mentioning again to emphasise, and I want to pick up on the water table. There is a page in your module booklet that talks about this. It'll be near the beginning somewhere. So just to remind you, we were learning last time about the water cycle and the fact that there are these inputs, outputs, stores and processes. Here we're interested in water under the ground, okay? The groundwater store is generally what we refer to it as in geography. Other people call them aquifers, A-Q-U-I-F-E-R, and you will hear that word. And you can also have this phrase water table, and they're kind of all very much interlinked, but we just need to use the terms quite carefully. So the water table is the upper limit of the saturated section. So if you look at the diagram in front of you, the blue means it's completely saturated with water. Above that, there is water, but it isn't saturated. There's also some air, hence zone of aeration. And the point about the water table is, ladies and gents, that it goes up and it goes down. And it goes up and it goes down purely dependent on how much water is being stored. So if it rained for the next 4 weeks, then the water table will go up and up and up and up and up. And if it didn't rain for the next 4 weeks, the water table will go down and down and down and down. So the water table moves, and that's a really important idea for us to understand, and it very much links to what we're going to be looking at in this video, which is the changing stores in the water cycle. So here is a graphic to try and get that across to you. Now this wouldn't really happen in the UK because in this diagram, when the water table goes down in the summer, there is no water left in the river because the water table is below where the rivers are. So that would mean that your riverbed is probably completely dry, and that would be incredibly unusual for the UK. Whereas in the summer, in the winter, the water table would rise and your rivers would have water in them. All I use this diagram to try and point out to you is that the water table goes up and it goes down, and it's purely dependent on how rainy the weather has been recently. Okay, so it's partly linked to changing stores, which is what this video is all about, and it's partly linked to what we did last lesson about the groundwater store. So I just wanted to mention that to you. But as I said, there is a page in your module booklet which talks about the water table, aquifers, all of that kind of stuff. Okay. One of the things that your exam board is really interested in and tends to ask quite a lot of questions about is changing stores in systems. So if you will accept that systems always have inputs, outputs, stores and processes, then the stores are going to be at different sizes depending on what the conditions are. And it's a fairly simple idea to get your head around, but of course we need some examples of that. So I've just given you one, which is the groundwater store. Depends on how much water is being stored underground, and that's going to depend on how much precipitation we've had. It's going to depend on how much infiltration and percolation there has been, because otherwise how is the water going to get underground? So if these are still kind of new words to you, maybe go back to the first video and be like, right, I need to get the hang of what those words mean, because otherwise all these other videos are not going to make a huge amount of sense. But we also take water out of the ground. If humans want water, one of the best places for us to get it is to dig a well into the groundwater store and suck water out of it. So we humans have a very direct effect on the water table and the groundwater store. I'm going to be talking more about that in other videos as well. Okay, so I would jot some notes down about this. There are some spaces in the module for you to do that, but equally a separate piece of notes that said something like changing stores in the water cycle would be really good. You can kick off with some diagrams, maybe annotate them. That would be a really good skill to practice as your first one. Right, you are looking at a diagram of a deciduous tree. D-E-C-I-D-U-O-U-S, deciduous tree. The opposite of that is a coniferous tree or an evergreen tree, a tree that has leaves on it all year round. Native trees in the UK generally are deciduous. They have leaves in the spring and summer. They lose their leaves in the autumn and winter. That is purely natural. It's nothing to do with human activity, this, but it is a changing store. And I need to remind you, of course, that plants are two stores of the water cycle, because you get water stored on top of the plant, which we call interception, and you have water stored inside the plant, which is called the vegetation store. Well, fairly obviously, both of those stores are going to be smaller when the plant does not have any leaves on it. So the seasonal change that we have in the UK affects two of the stores of the water cycle. Okay, so that's one thing you could talk about. This is a bit of a weird image until I explain what on earth is going on. What you are looking at is a whacking great big farm vehicle. I would imagine, I grew up on a farm, so it looks like a slurry tanker to me. But what the purpose of this picture is here. What's happened in the places where the wheels have gone over. And what's happened is something called soil compaction. The soil has been squashed by the weight of that vehicle going over the soil, and therefore you can see that the soil in those areas has been massively squashed compared to between the tyre tracks. That's going to massively slow down your rate of infiltration, the rate that water soaks into the soil, because all the particles are so squashed together. It's going to be really tricky for the water to be able to get in there. Less infiltration equals more runoff. More runoff equals higher chance of flooding, purely because runoff is the fastest route that water gets back to the river. If you ignore channel catch, which is where the precipitation lands in the river, but that doesn't happen to very much of the rainfall at all, so we don't have to worry about that one. Runoff could have, fairly serious consequences for flooding. And it's not just heavy farm vehicles that compact soil. It can happen on sports pitches, it can happen on footpaths, it can happen almost anywhere. Anything that squashes soil will slow down your rate of infiltration and is likely to encourage surface runoff, which is a bit of a problem for us. Okay. In terms of stores, less infiltration means less soil water storage, would mean less groundwater storage, and those kinds of things. So what you need to keep doing, I'm going to go back to last one, just the foundation of this module is learning the two cycles. Obviously at the moment we're only interested in the water cycle. We'll move on to the carbon cycle another day, but it's how they link together and remembering that it's a system. So if you change one thing, so we're talking here about this, infiltration, well, if there's less of that, there's more of that. But if there's less of that, there's less of that, there's less of that, there's less of that. All of these are linked together, and that is the most important idea that you can get your head around. We're back to our good old friend Impermeable Surfaces from video number 1. I-M-P-E-R-M-E-A-B-L-E, impermeable. What that word means is it doesn't allow water through, and humans are very good at creating impermeable surfaces. Because they don't allow water through, that has a huge impact on the size of our stores. If soil compaction reduces infiltration, well, that kind of stops it completely, doesn't it? So it's the same point, but kind of more extreme. And it's not just housing, it's roads, it's car parks, it's cycle path networks. There are many human things that create impermeable surfaces. Don't just limit yourself to kind of housing. We build all sorts of things which tend to be impermeable. And then, of course, having created all these impermeable surfaces, what we have to do is we have to drain them, because You don't want water hanging around on roads, that's dangerous. You don't want water hanging around on roofs, that's going to probably cause a leak. So we build these drainage systems, and a lot of people don't know, but drains like this that you find on the side of roads, they go straight to rivers. They do not go to sewage works, which is what a lot of people think. And just as a sort of public bit of advice, that means that any nasty chemically things that people put down these drains, they go straight to the river. So don't put anything nasty down these drains, please. They are designed to stop places flooding. They're not designed as somewhere that you can ditch your old tin of paint or anything like that, which people sometimes do. Anyway, that's a tangent. We build these drainage systems, and that's really good for kind of humans, but what it does dramatically is it puts more water into the river, so into the channel store, and it might be that so much water goes up into the channel store you might end up with a flood, and we will get to floods in a future video. Deforestation, a bit of a depressing photo, sorry. Deforestation is happening everywhere around the world, obviously famously in the tropical rainforest, but it is happening everywhere. If you can remember, please, that plants are two stores, which I keep going on about. They are interception and vegetation store. Cutting trees down has a huge impact on your water cycle because you're going to have more water in every other part of your water cycle if it can't be stored on or in the plants. Dams. We build dams for all sorts of reasons. We build them to create electricity. We build them to create reservoirs for water storage, for water sports. We build dams for loads of reasons. But obviously, it kind of goes without saying that what you have done is massively increased your surface store. And apparently, I don't know how true this is, we have built so many dams in the northern hemisphere that we have slightly affected the speed of the rotation of the earth. How bonkers is that? But you might need to check me out on that. It might be one of those myths that someone's told me and I've just remembered. Wells, this is a well, and this would kind of come full circle almost now. If you dig wells into the groundwater store and take water out of the ground, you are obviously going to reduce your groundwater store. Right, now there should be some stuff in your module booklet about the last two changing stores, which are very much linked together. Again, if you have already studied coasts, you will be vaguely familiar with everything I'm about to say now. If you haven't yet studied coasts, this might be a little bit trickier for you. We have this thing called sea level change, and we possibly think it's quite a new thing with global warming and climate change, but it isn't actually. Over the history of the Earth, sea levels have gone up and sea levels have gone down. This, obviously, impression is of the last ice age. And this is what we think the world would have looked like about 18,000 years ago. 18,000 years ago is when we were in the height, the maximum extent of the last ice age. So everywhere on there that's white, well, kind of a whitey creamy colour, would have been ice. Anywhere that's brown would have been land. So you can see that, particularly Southeast Asia would have been a very different place. You could have walked here across the Strait of Hormuz. If we zoom in on this area, look, we could have walked to Denmark. You could have had species easily migrating from mainland Europe to the UK. So we used to have a lot more ice than we have now. Therefore, this cryosphere, this word I introduced to you in video number 1, the cryosphere was bigger 18,000 years ago and the ocean store was smaller. But as you, of course, know, this is not true anymore, and the ice has now melted as the Earth has warmed up, and we've got less ice and more water in the sea. That, of course, is changing stores. And this little animation is just reminding you of the sequence of events. Okay, so during an ice age, the ice sheet grows, and then when the temperatures warm up, the ice melts and the sea level rises. Okay, so that's that. Quick bit of coast revision. There are two types of sea level change. There's this one, which is called eustatic, which is to do with the sea going up and down. And there is another one called isostatic, but that has no relevance to the water cycle, so I'm not going to mention it. Okay. Equally, I'm not going to mention thermal expansion, but if you want to do a quick bit of coast revision, you should remember that eustatic sea level change is to do with volumes of ice, but it's also to do with thermal expansion. But that is all explained in another video, so I'm not going to do it here. The second thing that's very much linked, and you should find some diagrams in your module booklet about this. So during an ice age, when the ice sheets grow, as you can see here, where does that ice come from? Like it's not like you can put water in a freezer and hey presto, you've got ice. Well, that is kind of what happens, but in a slightly more complicated way. So what essentially happens, ladies and gents, is because it's colder, because it's an ice age, instead of rain, you get snow. And you'll know a lot more about this after the third video, which is all about water in the sky. But instead of rain, you get snow. And what happens, folks, is because it's an ice age, that snow doesn't melt. It stays frozen and it gets squashed. And that, ladies and gents, is where glacier ice comes from. It is snow that gets gradually squashed over time. Now, it's possible, if you've ever played a snowball fight, that you've kind of recreated this process. If you're the kind of snowball player that gets a handful of snow and squashes it until you've got like the world's most lethal snowball, essentially you have recreated this process, but much more quickly. Okay, but it happens naturally, and the snow just gets squashed by snow falling on top of it, and it very, very gradually becomes the ice. So that is where ice comes from in an ice age. And then, of course, if we just link this back to the water cycle, so the water gets evaporated, it gets precipitated as snow, that turns into ice, and that's where it comes from. Okay, but of course, what we know now is that we've got more of this. The glaciers worldwide are not accumulating, they're not getting bigger, they are melting because of global warming, and therefore we've got that sequence of events where the ice melts and the sea level rises. And that is just a really important global scale changing stores. Okay. If you want to know more about glaciation and the water cycle, I have just included two short hyperlinks there. We don't study glaciation, some places do, and it might be that you're just like a bit confused or you want to know a little bit more about that stuff, so those hyperlinks may well be useful to you. Okay, now I am not going to dwell on these, I'm going to leave you to work your way through. If there are any questions on here that you can't do or you want to clarify, then you need to talk to your geography teacher about that and say, I was watching Nikki's video about the water cycle and I really don't know the answer to this question. So I'm just going to basically put them up on the screen. You can pause. The idea is that if you can answer these quite quickly and easily, you are doing well on the water cycle. If you're like, I don't know, then you might need to just have some one-to-one clarification. Okay, you can pause. I'm just going to kind of whiz through reasonably quickly. So this is a little bit trickier. We will keep returning to the differences between tropical rainforests and temperate grasslands in this module, or I should just say grasslands, because actually the picture you're looking at is a tropical grassland. A grassland is just somewhere, guess what folks, that mostly has grass in it. Pretty logical name. Tropical rainforest, located in the tropics, rains a lot, got lots of trees. they're named pretty logically, and we will come back to them quite often, to be honest with you. But this would be a really good little revision exercise to get used to all your different terms of like precipitation, infiltration, evapotranspiration. Maybe to practice that, you could just do this verbally, you could do it with another geographer, you could write it down, but practice using the terms to see if you could describe what the water cycle would be like in these two places and how and why it would be different. That would be really good revision. And then the last part of this video is just a reminder about systems. I'm not going to spend ages on this. And I know you're probably like, God, she goes on about systems all the time. Yes, I do. But the reason I do is because I know how important they are for physical geography, okay? So before you watch video number 3, there is a page in your module booklet that should have got some space for notes. Are we happy with inputs, outputs, flows and stores? I've used flows there deliberately because you can call processes flows or transfers. So there are 3 different words that mean the same thing: flow, process, transfer. So systems have 4 things. It's important to recognise that the flows or the processes or the transfers all happen at different speeds. We've talked at some length about that runoff is very fast and returns water to the river very quickly, and groundwater is very slow. I don't need you to remember any of these, but it's just to give you a sense. Look, if water goes underground, it might stay there for a few weeks. It might be there for thousands of years. If water goes into a lake, it's probably going to be there for a few years. If it goes into the soil, it's going to be there. So there's a sense that things happen at different speeds, which is worth just pausing and thinking about. And we have spent a reasonable amount of time in this video talking about the fact that stores will change over time and also in different places. So that's an important theory. The thing that hopefully you know from coasts is that if you change one part of a system, you will affect the rest of that system. And we have sort of been talking about that today, because if you, let's go back to this one. If you build a dam, you change the surface store, which will affect other things. If you cut the trees down, you lose your interception vegetation store. So we have got some examples of that, but it might be sensible in your module booklet to just jot a couple of examples down, make that obvious. And then we're going to really focus on this at the end of the module, so I'm not going to say very much today. But the other thing about systems is that they try to maintain equilibrium. They try to keep themselves balanced. And the best example I can give, and my students will be like, oh gosh, yeah, she says it all the time, is your body temperature. Your body is a system. It works best between 36 and 37 degrees centigrade. Your body is sort of constantly working to keep you at that kind of temperature. So if you go somewhere very cold, it works very hard to warm you up again. If you get too hot, it works incredibly hard to cool you down again. That keeps you in equilibrium, and fantastically, it keeps you alive, thank goodness. But I just want to remind you at this point that there are 2 types of feedback. And it's confusing because the words mean the opposite to what we expect them to. Negative feedback is good. Positive feedback is bad. Okay? Negative feedback is where your body goes too hot, cool down. Too cold, warm up. Negative feedback maintains equilibrium. We like negative feedback, okay? It's a good thing. Positive feedback exaggerates change. It makes things worse. And the best example that we are going to be the best example, yet terrible for humanity, is climate change. And we'll be looking at that. So if any of that is news to you, I would kind of maybe check that out before you go any further. And there's just a couple of other little revision activities that you might want to do in case if you're finding this module quite tricky because it's quite sciencey and maybe science isn't your favourite subject, unfortunately, there's no shortcut to learning it. It's going to be sort of revision and practice. So I just wanted to try and come up with some activities that might be quite useful to you. Okay, so pause obviously as much as you want to, rewind, and if you couldn't do any of those recap questions, talk to your teacher, please. Okay.